Hello! Today we're going to talk about Chapter 5.2, which is all about the modern periodic table. I know you guys already know about Mendeleev and how he came up with the general layout of the elements in the periodic table, but today we're going to start talking about trends that we see within the table. So to start, each element on the periodic table has a box that tells us information about that element. The basic ones contain 4 pieces of information. There is the name of the element, the symbol, the atomic number, and as you remember, the atomic number is the number of protons in that element, and then there's the atomic mass. And we've talked about atomic mass. We've said that atomic mass is the number of protons plus the number of neutrons. But you would think, if you're adding whole protons and whole neutrons, that your atomic mass would be a whole number. But quite often, the atomic mass of an element is not a whole number on the periodic table. So let's talk about why that is. It's because the atomic mass is actually a weighted average of the masses of different isotopes found in nature. What this means is, if we think about a carbon atom, carbon has 6 protons, and more often than not, it has 6 neutrons. But we could also have isotopes of carbon where there are more or less neutrons. So we could have one with 4 neutrons, we could have one with 5, we could have one with 7 or 8. But the most common is going to be the one with 6 neutrons. So if we have the one with 6 neutrons, and that is the most common, and then less common we have one with 7 neutrons, and then even less common we have one with 5 neutrons. What scientists do is they add these masses together. So this one would be 6 plus 6 is 12. This one is 6 plus 7 is 13. And this one is 6 plus 5, which is 11. They add those together and take an average, but they make sure that this one counts more than the others because it is more common of an isotope. That's why when we look at the atomic mass on the periodic table, it's often not a whole number, and we need to round in order to figure out exactly how many protons and neutrons there really are inside those atoms. Now, when we talk about atomic mass, it's not just about the number, it's also about the units. So the atomic mass is measured in atomic mass units, which, as we talked about before, is a super small unit of mass because atoms are so ridiculously small, it would be crazy to measure them in grams because it would be something like 0.00000 with 15 zeros. So scientists came up with an atomic mass unit. And what an atomic mass unit actually is it is 1/12 of the mass of one carbon atom. So if we took one atom of carbon and we chopped it up into 12 different pieces, whatever that is, 12 equal pieces, and we took the mass of one of those pieces, that is one atomic mass unit. And this makes sense because if you think about a carbon atom, the most common isotope of carbon has 6 protons and 6 neutrons, which means it has an atomic mass of 12. Divide that by 12, you get 1, which should be the mass of one particle, which is why we say that the proton and the neutron both have an overall mass of one atomic mass unit. Now, if this stuff isn't quite making sense to you right now, that's okay. We are going to talk about it more in class. It's actually kind of an interesting math issue. Moving on back to our table, it turns out that elements in the periodic table are arranged by increasing atomic number, meaning they're arranged by least amount of protons to the most amount of protons. But you can see that it's in this really funky shape. It's not just a box. And that's because the periodic table is actually arranged to show us trends or familiar patterns in these elements. Now, in order to understand these trends, we need to understand the format of the table. So, a few things to keep in mind is that when we're talking about the periodic table, the rows are called periods, so the back and forth are called periods, and the columns are called groups, the up and down. More often than not, we'll be talking about similarities between elements in a group, meaning a column up and down, but every once in a while we'll also talk about across a period. Now, the elements are arranged into these specific groups because the elements in a group have similar properties. So the reason why helium is in the same group as neon, even though they have very different atomic numbers, is because they have similar properties. And Mendeleev did this on purpose. And this pattern of repeating properties, meaning once you go past a group and come back to it, they have similar properties, that's called periodic law. Now, putting everything into groups like this, we come up with three main classifications of the elements. And these classifications are metals, nonmetals, and metalloids. Metals and nonmetals are pretty easy to define from each other, and they have very specific characteristics. Metalloids are kind of the weirdos that are in between and don't really fit either of the categorizations. So let's talk about what makes each of these unique from each other. Metals are always good conductors of electricity and heat. Of course, some are better conductors than others, but all of them conduct. They're solids at room temperature, except for mercury, and they're usually very ductile and malleable, meaning that when you change their shape, they don't break apart, they stay together and change shape, and we can make things like wires out of them. But the reactivity, how well these elements react with others, depends. We can't say that metals are all have a higher reactivity than nonmetals. We can't make a broad statement like that. We actually have to look at each individual element within these classifications. Now, nonmetals are poor conductors of heat and electricity. Many of them are gases at room temperature, although we do have some solids like sulfur. And these solids tend to be brittle and not ductile, meaning if I took a piece of sulfur and hit it with a hammer, it's going to break into a bunch of small pieces. It's not just going to bend to the shape of the hammer. And finally, we have metalloids, and metalloids are the weirdos of the periodic table because they're elements that share properties of both metals and nonmetals. For example, silicon is an element that is a metalloid, and it's used in circuit boards. And the reason it's used in circuit boards is because it's pretty lightweight, and it's a very good conductor of electricity, which means that it has properties of a metal. However, silicon is also very brittle. If you were to hit it with a hammer, it would not form into a new shape. It would actually break into a bunch of little pieces, which is a property of a nonmetal. So silicon is an example of an element that has properties of both classifications, which is why we have the in-between classification of a metalloid. Now, when we look at the periodic table, as we move across the period from left to right, the elements become less metallic and more non-metallic. So if we take a look at our periodic table down here, all of our metals are found over on the left-hand side, all the way over here. So you can see that the periodic table is mostly made up of metals. The nonmetals are over here on the right, and the metalloids are along this weird staircasey looking thing right in the middle, right here. So metals, nonmetals, metalloids. But it's interesting because the most reactive metals are found way, way, way over here in group 1, the very first group, way over on the left. But the most reactive nonmetals are found way on the opposite side, in the second to last column, or the second to last group, way over here on the right. Now, we're going to talk more about why this is. It has something to do with valence electrons and the outer levels of electrons. But just know for now that metals are on the left, nonmetals are on the right, and when you go to the extreme ends of those, that's where the most reactivity occurs. To finish up, I wanted to show you the homework questions because that's one of the things that came up in the video survey I gave you, is a lot of people mentioned they wish that I would give the homework questions in the video so they wouldn't have to bring their book home. And I'm going to try and do that in all the videos from here on out. So here are your homework questions. Please finish them for tomorrow.